In this video, we'll be going over concepts of K and what K means, so equilibrium concepts. So first of all, K is a physical property of a reaction. So you're going to have a very specific value for K for every type of reaction that can do equilibrium. And so it's also temperature dependent. So you can affect the K value or change the K. In fact, that's the only way to actually change the K value is to do the reaction at a different temperature, and then you could actually have a all new equilibrium constant. So, but in short, it's specific for each reaction. So just like enthalpy, like for example, when you have like an exothermic reaction and you get this, so and this is measured under standard states, then we have a measurable enthalpy, and that degree meant at standard state. So you'll have a set number, like a set enthalpy for every specific reaction. So the combustion of methane will be different than the combustion of propane, or the combustion of octane, etc. So um, reactions that you see go forward and backward, they're going to have their very own value for K. This is important, and it's a very simple bullet point here, but it's probably the most important thing to remember about equilibrium is that it's a ratio of concentration or partial pressure of product to concentration of reactant at equilibrium. And so this is the equilibrium expression. So we write it like this, and the general form would be like this, like y r makes X product. And so you actually take the concentration to the power of whatever the coefficient was. And solids and pure liquids do not appear in equilibrium expressions because equilibrium expressions only use pressures or concentration. So remember these brackets, they mean concentration. Or you could also write this in if you had partial pressure. You could also have these in torr or atmospheres. So you could have the partial pressure of the product to the power of x divided by the partial pressure of the reactant to the power of y. Okay, and it just depends on the problem. Like if they're giving you torr in atmospheres, then you should be solving for what's called Kp. And if they give you the problem in molarity and they don't specifically tell you to convert them to partial pressures, then you could just stick with what's called Kc. You might see a little subscript that says C there. So that little C means concentration, and that little P right there means pressure. Okay, but the point of this video was to go over the concepts of equilibrium, and the only reason I have this is to show that it's a ratio of product to reactant. So it's a way to quantify at equilibrium how much product you have compared to how much reactant you have. And it's very, very useful because it just wraps equilibrium up into like one number that you could just look at and you go, oh, well, that reaction must favor the product side, or oh, that reaction must favor the reactant side. And or you could see the value of K if it's incredibly small, like 10 to the negative seventh, then you'll go, oh, okay, so that's a ratio. So just remembering that that's a ratio, so of product to reactant, if this number is very tiny like that, then that means this number must be small and this number must be large. So we can tell that that reaction that does equilibrium with a K value of 10 to the negative seventh, we can tell that that largely favors the reactant side, greatly favors the reactant side. So let's put that in words here. So a large K value, so K greater than 1, means the reaction favors the product side. And a very large K, that is so large the reactants essentially become zero, is said to go to completion. So that would be, so if you have like a very large K, that's, I mean, at that point you just write a one-way arrow going to the product side. And then if you have a small K value, so or one less than one, actually, it means the reaction favors the reactant side. And here's a very simple little analysis you can do. So let's say your K value, and say your product is 1, like 1 molar, and your reactants are 2 molar, then our ratio here is zero point 0.5. So this number is less than 1, but if you look at the numbers that went into it, we have 2 on reactants and we have 1 on products. So that means our reactants are favored. Our reactant amount is greater than our product amount. Whereas if you have 2 over 1 and our ratio becomes 2 to 1 and our K value is 2, that means our product is 2 and our reactant amount is only 1. So in this case, our product side is favor. We have more products than we do reactants at equilibrium. So, um, and we'll be going back to this constantly when we go over equilibrium, like when we go over acids and bases and something called KSP, which is the solubility product. So that's equilibrium during a solubility reaction or a solubility process. So an example where combustion reactions, I wrote one a minute ago with methane. Combustion reactions with they have no measurable K. Essentially, the reactants become zero. So what happens like if we have a combustion reaction like this? Okay, and these, so when you burn methane, the gases that form, these are not gonna combine and then make methane gas again. That's not, it doesn't, like if you burn a log, the ash and all the gases that form, it's not coming back to make log again. So so those don't really have equilibrium because these essentially become zero when the reaction is done. So these get consumed fully. So if you tried, I mean, it would be silly, but if you tried, you'd have like, you know, zillions and zillions on the product side, but then on the reactant side, you would have zero. So this becomes undefined. You can't, I mean, you can't do that. So we just write a one-way arrow. So why study equilibrium? Why even go over this? Well, we're about to go over the next few chapters we cover, and topics that we cover are acids and bases, buffers, reactions of acids and bases, and then dissolvable processes, so solubility. And all these things, what they have in common is they take place in water. So why is that important? Is because the products are sitting there in water. So if you dissolve, so let's say we dissolve something that's known to be insoluble, it's actually, there is actually a measurable amount that actually is soluble. So if this guy dissolves, these two products, I mean, these two things, they're sitting there in water, so they're able to mingle together. Whereas when we burnt the log before, that's just free gas that forms, so that's not coming back. So in chemistry, we have a lot of reactions that happen in aqueous solutions, and then the products have a chance to mingle, and then they can result in a reverse reaction. And we'll see later on this year when we get to our second and third laws of thermodynamics and something called Gibbs free energy. This is largely determined by the energetics of the reaction. So which side, so our K value and which side it favors, it kind of depends on which side is more stable, which side is more energetically stable. Is it the reactant side or the product side? And this is kind of like the underlying explanation for the K values that we see. Okay, and I think this is a good spot to actually end this tutorial for equilibrium concepts. This will actually be, we could call this part one, and I'll be going over a problem that's we're gonna involve the mathematics of it, only because I believe it helps the concepts explanations as well at the same time. And so we'll be going over that in part two of our K concepts and equilibrium concepts. But for now, this is the end of our first tutorial on this in a two-part series for K concepts.